अस्सलाम वालेकुम। तो आज हम स्टार्ट करते हैं with the definition of the derivatives. So first of all, the definition of derives are a derived function, slope of the tangent lines, instantaneous velocity. The function is differentiable or have a derivative at a single point or not, and then a function is differentiable at a point is continuous at that point or not. So we assume that we have looked two situations whose resolution brought us to the same mathematical setup. First of all, the tangents and the velocities. As we looked at those two and limits, both ended up modeled by the following. जैसा कि हमारे पास एक फंक्शन था, एक पॉइंट say w, what is a q of s, that is a point of a function q is given, as well as two numbers s naught and w naught equals to q of s naught. We are asked to compute the limit, same limit but in two formats. The limit where s approaches to s naught, and we have a point, final point is a q of s minus the initial point q of s naught all over s minus s naught, or in other words, limit where h tends to 0. We have a small increment in s naught as a final point, that is a q of s naught plus h minus q of s naught all over h. So computing these limits is one of the reasons we study limits in the first place. The ratios q of s minus q of s naught all over s minus s naught and q of s naught plus h minus q of s naught all over h are called the difference quotients. So let us interpret all of this for tangents and for velocities as well. So start करते हैं by observing, writing out the difference ratios rather cumbersome. We need a slicker notation because in mathematics the notations ought to reflect what we are asked and what we are going to solve. For a function that a w equals to q of s looks like in either one of the two versions, q of s minus q of s naught all over s minus s naught, or q of s naught plus h minus q of s naught all over h. You may notice here that this s minus s naught is just replaced with h. Why? We will see in the coming slides as a change in w all over the change in s. We see that all we need is a slick notation for change in anything. So mathematicians invented such notations a few years back. It is written as a delta anything. We represent delta as a change in anything, a change in a point, and change in a 2 points in a function. So that for the function w equals to q of s, the difference quotient is written as the delta w, the change in w, all over the change in s. And for the most familiar function where we have y equals to f of x, we get change in y all over the change in x, as we have seen it in the functions and limits as well. So let's look at the picture. What picture says? We have 2 points. The first point is x naught of this original function y equals to f of x, and the second point is just x. And this first x naught is uh, the f of x naught, where we can interpret this in on x-axis this is x naught, on y-axis this is y of x, but y of x equals to f of x. So we have a function or a point here is a f of x naught, and the second point, the final point, is f of x. So hence we have this rise or run, the slope of the secant line, a secant line where a line touches 2 points of the function. So in limit we get the slope of the tangent line. If the function shown expressed as a quantity q of t that changes as time changes changes with respect to time, the difference quotient is the average rate of change over the time interval. That time interval is t naught to t, the change in time and the change in 2 points, where 2 points are the q of t naught and the q of t. We have the same function y equals to q of t. So in the limit we get the instantaneous rate of change. Here in this figure we can see that we have a point marked with P, and this point on x-axis we said that this point is point A, and we have a second point, we have a point we have marked this point is a x. So we have 2 points P and Q, and we know that the Q is approaching to P as close as it must be, and we know that the Q and P does not equal, but the 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 point Q is very close to point P. So we have on x-axis this point A, and on y-axis we say that this point is a f of A. So Q is a point x, but here we have the function of x, because this point x is a uh, independent variable, and this function is a dependent variable because this is a y function. So we can say that the function y equals to f of x is nothing but the function f of x, the final point, minus the f of a. So we can write here that m tangent, or slope of the tangent, is a limit where x tends to a, where x is approaching to this point a, x minus a, and this the y values indicated f of x minus f of a. When the quantity q of t represents distance traveled in time, we call the instantaneous rate change the instantaneous velocity at time t naught. All of these examples reduce to having to compute the limit. Examples हम देखेंगे कि limit of a difference quotient when the bottom approaches zero. So first of all, we formalize this procedure with the following: and velocity, other rates of change. We have a graph, and if we consider this graph of displacement, distance over time traveled, so we have distance in miles and time in hours, having 2 points marked on this function a and b. The average velocity can be found by taking change in the position of a and b, the change in distance delta s, and change in time delta t. So we can say that we have a run with respect to time delta t, and we have a rise with respect to the position function, that is delta s. So we can rewrite this formula by putting all these values as we discussed and seen before. that average velocity for this time, its average velocity equals to delta s over delta t equals to f of t plus delta t minus f of t, because it's a function of t, all over delta t. So the speedometer in your car does not measure the average velocity, but instantaneous velocity, the velocity at one moment in a time. So we can say that the v of t, velocity of with respect to time, the v of t equals to ds over dt, delta s over dt equals to limit where delta t approaches to 0, f of t plus delta t minus f of t all over delta t. So here are some uh, interesting derivatives. If we take the derivative, that the velocity is the first derivative of the position, we take the uh, derivative of the position. The first derivative is said to be the velocity, and if we take the second derivative of the position, that's said to be as acceleration. So it's a nice combination that the first derivative is the velocity and the second is the acceleration. And you see what will happen again. The example of free fall equations, we have just seen that s equals to 1 upon 2 gt square, and the gravitational constants are where g equals to 32 feet per second square, g equals to 9.8 meters per second square, and g 980 centimeters per second square. So we have s of 1 over t times 32 t square, where we have the value of this g is 32 and t square, and the s where we have 16 t square. So the v equals to ds over dt equals to 32 t. The speed is absolute value of velocity hence proved. The acceleration is the derivative of velocity, as we know. So a equals to dv over dt equals to the second derivative of s with respect to t. For example, v equals to 32 t, where a equals to 32. So if distance in feet, the velocity would be in feet per second, and acceleration would be in feet per second square. Velocity and other rates of change, we have a distance and a time with a function where at this point, the initial point from 0, when it is starting, so the acceleration is positive and velocity is positive, and both are increasing in positive direction. At this point, the acceleration is 0, velocity is positive and constant, and at this point, the acceleration is negative because it's getting smooth and going to the decrement or decreasing function. And at this point, all over the velocity is 0. This is a the top point. So acceleration is negative, velocity is negative and decreasing. The acceleration is 0, velocity is negative and constant at this point. So acceleration is positive and velocity is negative and increasing again, because the function is increasing from this point again. So the acceleration is 0 and velocity is 0 at this point. The rates of change, we have average rate of change, and is given by, as we have a limit of definition, a definition of limit, f of x plus h minus f of x all over h. Instantaneous rate of change, we have the derivative of this average rate. So we have f prime uh, of x equals to limit h tends to 0, f of x plus h minus f of x all over h. So these definitions are true for any function, as we will see in coming slides. So x does not have to represent the time here. For example, suppose that a ball is dropped from the upper observation deck of the Burj Khalifa from 450 meters above the ground. So we are to calculate the velocity of the ball after 5 seconds and the speed of traveling of the ball. How fast is that ball is traveling when it hits the ground? The solution to the problem, we have first of all the t naught and t equals to 5 here. When the ball hits the ground, so it's efficient to start the finding the velocity at general time t equals to a. So we have here t equals to a. Using the equation of motion, we have s equals to f of t equals to 4.9 t square. So we have v of a, because we have replaced t with a, v of a equals to limit h tends to 0, f of a plus h minus f of a all over h equals to, if we put all these values replacing the variable, limit h tends to 0, 4.9 a plus h square minus f of a, the original function is 4 point, this f of a is the 4.9 a square, t square means a square, equals to limit where h tends to be 0, 4.9. If we solve this a plus h square, we have a square plus 2ah plus h square minus the a square all over h. The limit where h tends to be 0, 4.9. If we solve this, a square positive and a square negative going to be cancelled out here, and we have just 2ah plus h square. So the remaining part is 4.9 2ah plus h square all over h. So the limit where h tends to be 0, 4.9. If we get common here, h, we get h common here. So 2a plus h, the remaining part. We put the value of h 0. So nicely we can say that we have 9.8a. So now we have the formula that the velocity after 5 seconds is v of 5 equals to 9.8 equals to 5 equals to 49 meters per second. So since the observation deck is 450 meters above the ground, the ball will hit the ground at the time t1 when s of t1 equals to 450. That is given as 4.9 t1 square equals to 450. This gives us as a t1 square equals to, as we take this value here, 4.9 is multiplying with t1 square. If we take this value on this side, we have t1 square equals to 450 over 4.9. टर्म यहाँ पे मल्टीप्लाई हो रहा है t1 स्क्वायर के साथ और यहाँ पे डिवाइड होगा, and t1 equals to under root, if we squaring both sides, so we will have t1 equals to under root 450 over 4.9. approximately 9.6 seconds. The velocity of the ball is hits the ground is therefore V of T1 equals to 9.8 T1 equals to 9.8 under root 450 over 4.9 approximately. If we calculate, so we have 94 meters per second square per second. So the derivative of a function, we have a function if that function is differentiable, if it has a derivative everywhere in its domain, that is the function is derivable. So we know if it is continuous and smooth, the function on closed interval must have one-sided derivative defined at the endpoints. तो ये क्या कह रहा है देखते हैं. ये कह रहा है कि एक function f of x that be defined near and at the point where x is equals to a, and the derivative of f at a is the limit where x is approaching to the value a or x naught. F of x minus f of a all over x minus a equals to the limit h tends to 0 f of a plus h minus f of a all over h. So if the limit exists, this is the condition. जैसा कि डेरिवेटिव्स को हम एज अ लिमिट फंक्शन लेते हैं, तो अगर लिमिट एग्जिस्ट करती है तो इसका मतलब है कि डेरिवेशन भी होगी और डिफरेंशिएबल फंक्शन है. अदरवाइज अगर टू साइडेड लिमिट्स एग्जिस्ट नहीं करती तो फंक्शन भी डिराइवेबल नहीं होगा. हम देखते हैं द नोटेशंस about this is when the limit exists, we denote its value that clearly depend on the function and by a. So f prime of a is also f dot of a, and by the Leibniz notation we have the derivative of y with respect to x, where we have the point s x equals to a. This a is the point where the function is derivable or anything else that indicates the better by the way of notations. So compute the above limit using the function with the position or point a. So we have finally the definition of limit where h tends to 0. F of a plus h minus f of a all over h is called the derivative of a at the point, derivative of f at the point a. So we write as the notationally correct f prime of x where equals to limit h tends to be 0 and f of a plus h minus f of a all over h. So the derivative of f with respect to x we are assuming here. There are many ways to write the derivative of y equals to f of x, and these ways are notations we will discover in coming slides. So the basic notations, because notations ही हैं जिनकी मदद से हमें पता चलता है कि मैथमेटिक्स में क्या बात हो रही है. सो इट्स अ मैथमेटिकल लैंग्वेज. इसको हम थोड़ा सा जानने की कोशिश करते हैं यहाँ पे कि एफ सिंगल प्राइम, यहाँ पे ये जो कामा है ये सुपरस्क्रिप्ट में, इसको हम पढ़ते हैं एज अ एफ सिंगल प्राइम और एफ प्राइम ऑफ एक्स और द डेरिवेटिव ऑफ एफ विद रिस्पेक्ट टू एक्स. दिस इज अ equals to as a y prime. Y prime means f of x or f prime of x. So it's also equals to dy over dx. All these notations represent the derivative with respect to x here. So the derivative of y with respect to x, df over dx, or we can say the derivative of f with respect to x, or d over dx f of x. So we can say that the derivative of f of x here. अच्छा जी, तो नोट फरमाएं Okay, dx does not mean here that a d times x. This is just notation which represent the change in x or the derived function of x here. So it does not imply that the d times x, and dy does not mean that d times y, and dy dx does not mean that a dy divided by dx, except when it's convenient to think of it as a division. And df over dx does not mean that a df is divided by dx. Okay, the d to the dx f of x does not mean that the d over dx times f of x. So we have a function with a slope of original function y equals to f of x, having some breaking points here. These points are said to be an open interval because it starts from the 0 and ends at this point 1 and 2. And similarly, this point starts from here and ends at this point 3 and 4. So what does it suggest? If we take the derivative of this function, y equals to f prime of x, we will have the function and the shape that it starts from the initial point 2 ends to the 1, where at this 0 point, this line of y, it is a closed interval, and at this point 1 and 2, it's open interval, as we have seen just in intervals. So we will discover it in the coming slides. We have a function where y equals to x square minus 3. As we see that this parabola is a graph of shifted down by 3 units. So we will solve this by deriving y prime equals to limit where h tends to 0, and we have x plus h square minus 3 is by the formula. Wherever we see x, we replace it by x plus h, and this quantity is squared. So x plus h is squared and minus 3, and this minus is by the rule, by the formula. So we have an original function f of x, that is the f of x equals to y equals to x square minus 3, x square minus 3 all over h. So we have y prime where limit uh, of h tends to 0, 2x plus h. By solving this, we will have that x square plus 2xh plus h square minus 3 minus x square minus 3. This minus 3 will be the minus into minus plus 3. This minus 3 and plus 3 will be cancelled out. This x square and this minus x square and plus x square will be cancelled out, and we will have just h in common. So 1 upon h will be out front, and we will end up with 2x plus h. This is a simple algebra. So by putting the value of h as 0, we will just end up with 2x. So the 2x will have the slope at this point 0. The function is differentiable or not at a single point. So that point can be smooth. For the differentiability, the function must be continuous and smooth. What are the points where derivatives will fail to exist? These points are corners. We have this function as absolute value of x, f of x equals to absolute value of x. And we can see that this function is a value of one positive side and one negative side, ending at or meeting at the zero, where zero it makes a corner, and this is the point where the limit does not exist and the derivative does not satisfied. And we have a cusp here. कस्प हम उसको कहते हैं जहां पे एक फंक्शन आकर रुक जाए और उसकी साइन चेंज हो जाए। अगर ये पॉजिटिव साइड से आता है और जीरो तक, जीरो से फिर नेगेटिव साइड तक जाएगा, तो पॉजिटिव से नेगेटिव साइन इसकी चेंज हो जाएगी। इस साइन की चेंजिंग्स को हम एज अ कस्प कहते हैं। तो ये जैसा कि फंक्शन है हमारे पास वो है एफ ऑफ एक्स इक्वल्स टू एक्स टाइम्स 2/3, and vertical tangents is given by a function f of x equals to third root of x. So at this point जहाँ पर जीरो है, यहाँ पर वर्टिकल टेंजेंस में और जीरो पॉइंट पर लिमिट एग्जिस्ट नहीं करती और फंक्शन कंटिन्यूअस तो है पर is not differentiable. And at the discontinuity at this point, ये जो कंटिन्यूटी का ग्राफ है, हम इस पॉइंट ये पॉइंट्स जो हैं ये एफ ऑफ एक्स इक्वल्स टू एब्सोल्यूट वैल्यू ऑफ एक्स को ही यूज करके बना सकते हैं। और यहाँ पे हम देखेंगे एक फंक्शन जो लेफ्ट साइड से आ रहा है वो -1 पे एंड हो रहा है एंड सेकंड फंक्शन स्टार्ट हो रहा है हमारा 1 से। वेयर एवर वी हैव द x less than 0 we have a -1 function, and wherever we have the x is greater than or equal to 0, where we have equal to 0, so this is a closed interval, this will be always 1.